We've now talked about several different modes of convergence for sequences of measurable real-valued functions. There's almost sure convergence, convergence in L1, convergence in L2, and most recently, convergence in measure, or convergence in probability in a probability space. In this lecture, we're going to talk about some of the relations between them, furthering what we saw last time. Let's return to Lp. We've already made a careful study of L1 and L2 basics, and we have mentioned this space Lp before. Given a measure space and a real number p bigger than or equal to 1, Lp of that measure space is the set of measurable real-valued functions, which we now have a notation for, L0, with the additional property that the integral of the pth power of the absolute value of f is finite. Now, what we haven't shown is the important fact that this quantity, taken pth root, is actually a norm, which implies that this is actually a vector space. So that's a theorem here I'm going to state. The Lp norm, which is defined to be the pth root of the pth integral, actually defines a norm on this space. Now again, to be careful, what we mean by a norm on this space is on this space modded out by mu null sets. We have to identify two functions that agree on a set of full measure. Provided we do that, then this actually is a sub-additive function, which is 0 if and only if the function is 0 almost everywhere. We proved that in L1, it's almost definitional from the integral, and from L2, that's what we used the Cauchy-Schwarz inequality for. It turns out it's true for all p between 1 and infinity. We could spend a lecture proving that with some fun convex analysis, but we're not going to. Lp will play a very minor role in what we do going forward, other than the critical cases p equals 1 and 2. Later on, we'll add infinity, and that will also be important to us. If you're interested, their details are in this theorem. This result, the sub-additivity of the p-norm, is called Minkowski's inequality. We're going to use Minkowski's inequality, that is the sub-additivity of the Lp norm, in this lecture. If you don't like using a theorem that we haven't or aren't going to prove, you can just restrict your attention where we use it to the cases p equals 1 and 2. In fact, p equals 2 is the only case where it has real probabilistic application in what we're going to do this year. Now, let's look at convergence in Lp. Given a sequence of Lp functions, we can talk about convergence in Lp. Since the Lp norm is a norm, it defines a metric just by taking the norm of the difference, and so we have the usual notion of convergence in this metric space. Fn converges to f in Lp if the norm of the difference tends to 0. We can add that now to our list of different kinds of convergence and compare it to the other ones. And here's the first comparison that I'd like to make. If Fn and f are in Lp, and if Fn converges to f in Lp, then in fact Fn converges to f in measure. This is an easy application of Markov's inequality, which we stated already with a p in it. Markov's inequality says that for any epsilon strictly greater than 0, the measure of the set where a non-negative measurable function, like the absolute value of Fn minus f, exceeds epsilon, is less than or equal to 1 over epsilon to the p times the integral of that non-negative function. But that's 1 over epsilon to the p times the Lp norm of Fn minus f to the power p. And our assumption is that that tends to 0. Since that holds for every epsilon, we conclude that Fn converges to f in measure as well. So, like almost sure convergence, Lp convergence for any p is stronger than convergence in measure. And, like almost sure convergence, it is strictly stronger. The converse is false. Consider this kind of counterexample, which I'll let you figure out how to extend to other measure spaces. Suppose that our measure space is the unit interval equipped with the Borel sigma field and the Lebesgue measure, and consider this sequence of functions. They are indicator functions on shrinking intervals, adjusted so that the total area underneath is 1 for each n. Well, I claim that this sequence of functions converges in measure to 0, that is, in Lebesgue measure, because the Lebesgue measure of the set where the absolute value of fn is bigger than or equal to epsilon, that's going to be less than or equal to the Lebesgue measure of the set where fn is bigger than or equal to n, for any n bigger than or equal to 1. The reason being that the function fn, if it is positive at all, is greater than or equal to n. But that is exactly equal to 1 over n, and that, of course, goes to 0. That's true for any strictly positive epsilon, and therefore this sequence of functions converges in Lebesgue measure to 0. Now, does it converge in LP norm? Let's just check. Fn minus 0 in LP norm to the pth power is the pth integral of Fn. Well, that's just the integral over the interval from 0 up to 1 over n of n to the p, which is 1 over n times n to the p, since this is just a Riemann integral, after all, given that the function is constant. So that's n to the p minus 1, and therefore the LP norm, taking the pth root, is equal to n to the 1 minus 1 over p. And since p is greater than or equal to 1, this certainly does not go to 0. In the case p equals 1, it stays constantly equal to 1, so the distance from fn to the 0 function is constant, definitely doesn't go to 0, and if p is bigger than 1, this distance actually explodes. So we see that convergence in measure can occur even when LP convergence fails for every p. Now, despite that disconnect between the two, we're going to use the properties of convergence in measure to prove a big theorem now that I've alluded to before, and that is the LP spaces are actually complete metric spaces. They are Cauchy complete. If Fn is a sequence of functions in LP that is Cauchy in LP, that is, if the difference between different terms goes to 0 in LP as you go further down the sequence, then there actually is an LP function that that sequence converges to. Let's prove this. So first of all, as with convergence, as we showed on the previous slide, LP Cauchy sequences are Cauchy in measure. And the proof is almost exactly the same. The measure of the set where Fn minus Fm is bigger than or equal to some tolerance epsilon by Markov's inequality is less than or equal to 1 over epsilon to the p times the integral of Fn minus Fm to the p, and that is equal to the pth power of the LP norm of the difference between Fn and Fm, which we know tends to 0 as n and m tends to infinity, which shows that Fn is L0 Cauchy as claimed. Now here's the key point. Last time we showed that any L0 Cauchy sequence has an almost surely convergent subsequence. There exists a subsequence Fnk that converges almost surely to some function f, which is measurable. Great. What we're going to do is show that that f is actually in LP, and that the convergence of this subsequence, and hence by the Cauchyness, the whole sequence, is also in LP, concluding the result. So we'll just measure for this subsequence the LP distance between Fnk and the almost sure limit f. Of course, at the moment, this could just be infinity because we don't even know that f is in LP. So we're going to compute this to show that it's not. Not only is it not infinite, but it tends to 0. That is the integral of the limit as j goes to infinity of Fnk minus Fnj to the p. Okay, that's just because f is the almost sure limit of the subsequence fnj, and of course taking this function of it is a continuous function, and so we still have the almost sure limit inside here. So what we need to do is exchange a limit and an integral, and we have lots of tools for doing that. Here I'm going to use Fatou's lemma. Fatou's lemma says that a lim_inf on the inside and a limit is a lim_inf can be pulled outside the integral at the expense of possibly increasing the value. So this is less than or equal to the lim_inf as j goes to infinity of the integral of fnk minus fnj to the pth power. Well, that is, by definition, the lim_inf as j goes to infinity of the LP norm of the difference between those two to the pth power. We did that calculation for fixed k, and what we're interested in is the limit. So the limit as k goes to infinity of this is less than or equal to the limit as k goes to infinity of the lim_sup as j goes to infinity of that difference. But now we see that that lim_sup can be taken to be just a limit because of our assumption that the sequence fn is LP Cauchy. If a sequence in a metric space is Cauchy, then all of its subsequences are as well, and that means that this double limit is equal to 0. And so we have now concluded that the subsequence that we chose using convergence in measure actually converges to this almost sure limit in LP. But the original sequence was LP Cauchy. If you have a Cauchy sequence that has a convergent subsequence, then the whole sequence is convergent. To see that, we just do the usual estimate that for any term in the sequence, fn minus f in LP is, now here's where we're going to use the subadditivity of the norm. This is inside fn minus fnk for any appropriately chosen term in the subsequence plus fnk minus f, and by the subadditivity of the LP norm, that's less than or equal to fn minus fnk in LP norm plus fnk minus f in LP norm. Now we've just shown that this goes to 0 as k goes to infinity, and since the sequence is LP Cauchy, this goes to 0 as n and k go to infinity. So as long as we choose the nk's, which we have total freedom to choose here, so that both of the indices go to infinity, we will get the convergence that we want. Again, if you don't like the fact that we're using subadditivity of the LP norms, we're only going to apply this result later on in the case where p equals 2. So we've already covered that. And there we have it. LP is a complete norm space, also called a Banach space. To keep track of all of the different kinds of convergence we've now talked about, let's put together a summary chart. We've talked now about, of course, almost sure convergence. We've talked about convergence in measure. Before we talked about L1 and L2, and now we've talked more generally about LP convergence. Let's look at the relationships between these. Over the last 2 lectures, we showed that almost sure convergence implies convergence in measure, always. We also just proved in this lecture that LP convergence implies convergence in measure, always. What about the converses of those? The converses of those are generally false. Convergence in measure is weaker than almost sure or LP convergence. But we do have some partial converses if we have additional assumptions or if we restrict our view. For example, the key feature that we've used several times now and will use again is that we can go from convergence in measure to almost sure convergence provided we're willing to pass to a subsequence. That is, any L0 convergent sequence has a subsequence which is almost surely convergent. Of course, we can follow the arrows in this diagram and therefore see also that any LP convergent sequence has an almost sure convergent subsequence. Great, so we can get from LP to almost sure, at least by passing to a subsequence. What about the reverse direction? Can we go from almost sure convergence to LP convergence? Well, typically not, but we do have a tool that will allow us to make that passage under the appropriate circumstances. And that tool is the dominated convergence theorem. We think of that usually in L1, but LP is just the space of functions whose pth power are in L1. So if I have an almost surely convergent sequence of functions and they have a uniformly dominating LP upper bound function, then the dominated convergence theorem will allow us to go from almost sure convergence back to LP convergence. So this diagram is nearly complete. We can go backwards or forwards under the right circumstances everywhere, except for one arrow that we haven't yet discussed, which is here. Can we, under the right conditions, go from convergence in measure to LP convergence? And the answer to that is yes, and the result is also known as the dominated convergence theorem. Here is the L0, L1 dominated convergence theorem. It looks very similar to the one that we already proved. Suppose that I have a sequence of functions fn and a sequence of dominating functions gn, so that gn dominates the absolute value of fn, where the gn's have a limit, but now we'll only assume that that limit is a limit in measure. We'll also assume that the fn's have a limit in measure. Now, as in the usual dominated convergence theorem, the dominating function, which is the limit of these dominating functions, should be in L1, but we won't know a priori that the f, which we're trying to conclude something about, is in L1. And finally, we will assume that the integral of the gn's converges to the integral of the g. Under those circumstances, we will be able to conclude that the limit in measure of the fn's is actually an integrable function, and that the integral of fn converges to the integral of f. In fact, we have, as we had before in the dominated convergence theorem, if we cared to state it that way, the stronger statement that fn converges to f in L1. As before, a typical, simpler, weaker statement of this result is the case when gn is constantly equal to g. So that would just say, suppose I have a sequence of L1 functions that are uniformly dominated by an L1 function, and suppose that fn converges in measure to some function f. Then indeed we can conclude that that f is in L1 and that fn converges to f in L1. We're going to prove this now. The proof actually just applies the usual dominated convergence theorem after we pass several times to subsequences, because convergence in measure assumptions here can be converted into almost sure convergence assumptions that we have in the usual dominated convergence theorem conditions after passing to subsequences, and then reassembling back to the full sequence. So let's lay out those details. By assumption 2, we can find subsequences fnk that converge to f and gnk that converge to g almost surely. Now, to be clear, if we did those separately, they would have different indexing sets. So what we usually do is first we'll find a subsequence of indices for which the fnks converge almost surely, and then we'll choose a subsequence of that for the g's so that the two will converge along the same subsequence of indices. Now, using that, we can compare the absolute value of the limit function f to the limit function g. And the way we can do that is noting that by what we just stated, f is the almost sure limit, as k goes to infinity, of the absolute value of fnk. But fnk is less than or equal to gnk, and therefore, by the squeeze theorem, we have this inequality almost surely as well, but that limit is equal to g. So we do get that the absolute value of f is almost surely less than or equal to g. So we're setting ourselves up nicely for the usual conditions for the dominated convergence theorem. But to really make this proof as slick as possible, we're just going to argue by contradiction. We will suppose, for a contradiction, that the statement we wish to conclude, that is, that fn minus f converges to 0 in L1, is actually false. Okay? Well, what does that mean? that means that this sequence of real numbers doesn't converge to 0. That is, that there is some small but strictly positive epsilon and some subsequence of indices nk, which may not be the same sequence that I used above, but I'm just going to use that again to denote a subsequence, such that along that subsequence, this distance does not drop below epsilon. That's what it means for a sequence not to converge to 0. Infinitely often, it stays above a limit above 0. Okay, however, our assumption is that Fn converges in measure to F, and of course convergence in measure passes to subsequences. So Fnk also converges in measure to F, and because of that, we can pass to a subsequence. Therefore, we will choose another subsequence, which I'm still kind of sloppily going to call Fnk, that converges to F almost surely, and for which Gnk also converges to G almost surely. We should probably have Fnklmr at this point. You can see why I'm not changing notation. I'm just generically referring to nk as some subsequence as we go, changing from line to line. That is a sloppy but standard kind of notation in this area. Okay, now we're set up to really use the normal dominated convergence theorem, because we can note that the difference between f and fnk in absolute value by the triangle inequality for real numbers is less than or equal to the absolute value of f plus the absolute value of fnk. By what we proved above here, that is less than or equal to g plus gnk. And as k goes to infinity, that converges to 2g, almost surely. And also, we know that the integral of g plus gnk, which is the integral of g plus the integral of gnk, by assumption 3, converges to the integral of 2g. And so we are exactly in the case where the regular dominated convergence theorem applies to conclude that the integral of f minus fnk tends to 0, which is an explicit contradiction to this. And therefore, our original assumption that this doesn't converge to 0 must be false, and we've concluded that indeed Fn converges to F in L1. And finally, to conclude from there the usual statement that the integral of Fn converges to the integral of F, we just note that the absolute value of the difference between the integral of Fn and F by linearity is the integral of Fn minus F, absolute value, which is less than or equal to the integral of Fn minus F, which we just showed goes to 0. So there is the dominated convergence theorem for convergence in measure. By the way, there's also a convergence in measure version of Fatou's lemma, but this, being the more powerful tool, will satisfy us in any situations where we need. That pretty much concludes what I wanted to say about the different forms of convergence of measurable functions. At least for now. We will come back to talk about yet another form of convergence, convergence in distribution, a little bit later. But before we get there, we need to tackle one more measure-theoretic topic with a more probabilistic outlook: product measure and the multiplicative systems theorem.